working, so I guess there's some way to maximize this. Maybe you know that?
Yeah, you just hit present. There we go. Cool.
Sound good?
Yeah.
All right. Thank you very much. So thanks everyone for coming. So today's seminar, we have Jim Halverson, all the way from Northeastern, in person, and he'll be talking about quantum field theory and neural networks. Yeah, we can record.
All right. Hello, everyone. Thank you for the invitation to be in person. I was excited about that because, like all of you, I've given so many Zoom talks over the last year. So speaking in person's a new luxury that we've started to enjoy again this semester. So the title of my talk is called Building Quantum Fields Out of Neurons. It's based on some work that I've been doing, but heavily inspired by some work I did with my students last year and this year, and some related work in progress with some other friends. So the backdrop is that there was a cool meeting that we held at Microsoft in 2019 on ML and physics. And there were some results that appeared there that I'll tell you a little bit about today that sort of made the physicists say that just sounds like quantum field theory. And I'm going to build on that. So that was what inspired this. To tell you quickly, my students are wonderful. Maybe I can move this. My students are fantastic. Anandita is graduating in 2 years and is going to be looking for physics postdocs, and Keegan is graduating this year and is going to be looking to join an ML lab. There is also a lot of growing interest in this interface, and if you're not connected and want to be, there's various ways to be connected. So Physics Meets ML is the virtual seminar series that follows up the meeting we held at Microsoft in 2019. Virtual seminar series with people from industry and from academia. There's the NSF AI Institute for Artificial Intelligence and Fundamental Interactions that I'm a part of. There's a lot of NSF AI institutes out there, but this is the one at the interface with physics. And the questions are sort of the obvious ones you would expect. Can machine learning help physics and math discoveries? And can physics and math help understand ML in different sorts of ways? And if you have questions, you should feel free to reach out to me also. Okay, so just a little bit of context. So the way that I think about this broadly is that we, as high energy theorists, normally live our lives here at the intersection of math and physics with all sorts of influence going both directions. And there's a list of things here that in this audience I don't need to review. But I think something that's happening is that computer science is growing more and more mature. It's a very young field compared to math and physics. And so what's starting to happen is that more and more advanced computer science is starting to get woven into these subjects. There's some work that I've done with friends on ML for knot theory. There's something called SAT solvers that are leading to new types of proofs that can appear in math. People are using reinforcement learning for automated theorem verification. There's all sorts of things that you've heard about using sort of empirical aspects of ML to get at physics results. And what I'm going to try to do today is instead use some theoretical things in the machine learning literature to try to talk about some of the things that we know and love. So this is theoretical ML for QFT. One thing that I should mention is that a major player in all of this is neural networks. So you've probably seen many of these results. You may know that the best Go player in the world is now a reinforcement learning algorithm called AlphaZero. There's a movie about it. There's standard things like on the left, this is called supervised learning, where a neural network learns to make predictions about images. It's the major pipeline that maybe you've heard of. There's natural language processing. Maybe you saw these things arise out of OpenAI last summer, where the AI will complete some prompt and give a rather convincing screenplay or something like that for half a page. And then there's also generative models. So this is an example where a neural network is trained to take some noise from some noise distribution, like a multivariate Gaussian, and produce something from some data distribution that you care about. It's a sampler, if you'd like. You're learning to simulate a system with a neural network. And this is one that it generated. This thing's called, the network was called a vector quantized variational autoencoder. And this is an image that looks like a person. She is, someone that is pretty convincing that this could be a person, but this is actually not a person that exists. So all of these sorts of different techniques are powered by neural networks, and all of them are starting to make their way into the natural sciences.
So it just generated that image from
This image is generated from noise.
Wow.
Yeah.
Not a cat.
I mean, I guess if you trained it on noisy cats, it could be able to.
What's the picture for the natural language?
Yeah, good. So very good. Why is that good? The most famous natural language architecture from the last few years is called the transformer. Hence this. For reference, this is an enormous field. One way to measure that is the paper from 2017. It's called Attention is All You Need. And it has more citations already than any paper in the history of high energy theory. So this is not a comment about importance of the work. It's a comment about size of the community. And so it's really a big community. All right, so those are not the things I'm going to talk about. This is just to remind you that what's been happening in machine learning is pretty powerful and also is being increasingly employed in the natural sciences, and neural networks are sort of the backdrop of all of it. So I'm going to give you a theory talk today because I'm a theorist and you are too. So the linchpin of what I want to talk about today is to recognize that neural networks are random functions, and they're random functions based on how they're constructed. So there's something called an architecture in a neural network where you take some tiny functions and you stitch them together into a bigger function via composition. There's parameters that appear, and the sense in which a neural network is a random function is based on the fact that it has random parameter draws appearing in it. On the other hand, quantum fields are random functions in the path integral, for instance, in the Euclidean path integral. They're drawn from a particular probability density on function space, e to the minus s. So quantum fields are random functions also, and a priori, just saying that much, there's no reason that these things should have anything to do with each other. But one thing that has happened, there was some results in the 90s, and there's really been an ML burst in the last 5 years that suggests that these things are actually more closer than you might expect. And in particular, my previous work on this subject is sort of how to take ideas from QFT and imprint them on ML. And in this talk, this is the first time I'm giving this talk, I'm going to try to take it the other way. So can we use ideas from neural networks to try to engineer actual quantum field theories? Okay, I'll ask in a minute if there are any questions. But the outline of my talk is to talk about generally what I would mean by building quantum field theories out of neurons and how that is different from what we normally do. If we're going to do this in any kind of realistic setup that will map onto stories, not today, but eventually stories that we care about, we should be able to talk about symmetries, and in particular, since we'll be in Euclidean, we'll talk about Euclidean-invariants. Then I'll tell you a story called the NNGP correspondence, which is a story about Gaussianity and how in certain large N limits, neural networks are drawn from Gaussian distributions on function space. To actually have a quantum field theory defined by this, we need to have some properties satisfied that are related to having a unitary quick rotation, Lorentzian theory. And then I'll tell you a little bit about how in some of these systems at large N, there are theories, two different architectures that at large N give exactly dual statistical ensembles. And finally, given the Gaussian story, I'll introduce non-Gaussianities. There's two places where non-Gaussianities arise. The Gaussianity arises itself from a central limit theorem. So if you want non-Gaussianities, you need to break the assumptions of the central limit theorem. And that's what I'll do. And finally, I'll make some comments and predictions about why I'm interested in this and what it might be useful for. And that's the outline. So any questions so far? Yeah.
So when you say to engineer QFTs, are we just interested in a different way of describing QFT? We're interested in finding new field theories?
I'm going to give you a different way of thinking about quantum field theories, where there's going to be choices to be made that affect the correlators, just like how when we do phenomenology, we choose Lagrangians. Sure. Okay. Yes.
Yeah, you mentioned there's some idea from early 90s.
Yes, mid 90s.
Yeah, I wonder like what's the reason it's now developed that much?
Well, it's developed a lot in the last 5 years, but it was dormant for about 20 years. One reason is that for many years, neural networks were out of fashion. They were not doing particularly well from the perspective of machine learning relative to other techniques. The paper in the 90s that was important connected neural networks to Bayesian techniques, and the Bayesian techniques were much more the rage then. But as neural networks have started to reemerge, especially in the last 10 years, recognizing this theoretical connection has been of increasing interest. So the first paper that I'm thinking about in the new generation of this wave is sort of 2016, 2017. Anyone else? Okay. All right, so I'm just going to go through each of these sections, and I'll ask for questions after each. Feel free to interrupt me as well. So I'm going to build quantum field theories out of neurons, and so I need to flesh out the essential idea and how it's different from what we normally think about. So this is what I'm going to do. I'm going to consider my field phi, which I have given a canonical Greek letter that we care about. It's going to be a real scalar in this description. And I'm going to build it by taking it as a sum of AI, HI. These HI of X's are what I will call the neurons in this talk. And these AIs are some parameters that are drawn from some distribution PA, where I make some assumptions about the moments. And it's already clear here that even if the HIs were completely deterministic functions, the phi I, this phi itself is a random function with some intrinsic randomness coming from the fact that I drew these parameters from some distribution. Okay. In reality, the neuron HI can itself be a very complicated object, and we'll talk about that, and it has its own parameters. So there's parameters in HI, and there's parameters here, these A's, and together these parameters endow phi itself with some randomness. Okay. Oh, there is a slide issue where things seem to not be quite, I won't worry about it. If it keeps on, I'll try to fix it. But the point is that this is a different origin of randomness. So the normal way to think about it in the path integral is that we have some density on functions that is e to the minus s in the Euclidean theory, s of phi the action. And every field phi, every concrete field is, you can think of as a draw from that density. And then of course we compute correlation functions across the ensemble of scalar fields phi associated with the density. The point here is that this is a totally different construction. The origin of randomness is not based on the distribution from which we draw it, the function space distribution, that's our Euclidean action. The origin of randomness here is by construction, where I build my field out of these little widgets and there's parameters appearing, and this is why phi is a random function.
What is the inner product between HI and HJ?
The inner product between HI and HJ?
Yeah.
Where's HJ? You mean if you had two H's? Yeah, you can, right. So this thing is canonically called the post-activation. The inner product there, this thing is just living in Rn for some n. So it's the standard inner product on Rn.
No, but they're not orthonormal or anything like that.
Not a priori, no. So the HI itself has its own statistics because it has its own parameters.
Yeah, I understand, but fixing those statistics, I'm just trying to match on to the usual normal mode expansion of a field that we would do in a path integral. We would, expand phi in some basis of modes.
Yes.
We'd have some coefficients AI that we integrate over.
Yes.
And the HI would be, if we're doing free field theory, would be modes of some classical differential operator.
Yes.
I'm just suggesting that it looks very similar to that, where the differential operator is the one whose eigenfunctions are H.
Yes, in that case, those eigenfunctions are in the normal scalar field are complex exponentials. Yeah. And in this case, these H's will be potentially very complicated functions that are not simple complex.
Yeah, so it's like you're like doing the Laplacian on a different manifold.
Sure, yeah, might be. I haven't thought about it from that perspective.
In that sense, is it not the same origin of randomness, right? Like, it's a path integral over the Fourier modes, either if I d phi, I can think of it at either position space or momentum space. I mean, it would be like drawing from d phi of p for every p, but with fixed functions hi of x, which are just like the ikx or whatever.
Yeah, I mean, if you want to think of it in a mode expansion, maybe that's a different way to cast it in the same language, but it's not just drawing it directly from the function space density. That's my point. So Neil's work, the point of Neil's work, this work that I mentioned from the 90s, is to provide a function space description of neural networks. And here instead, we normally think of quantum field theories in function space themselves. We're going to try to give a parameter space description of QFTs. Okay. So because the action is not going to be central here in any way, shape, or form, this is non-Lagrangian. My slides, sorry, they got messed up. I don't know why. The point is that we can compute correlation functions, and these correlation functions can be computed in parameter space. Normally, we would compute these in a path integral, but here, if we have parameters theta that appear in these functions f, we can compute correlators by integrating against the distributions from which the parameters are drawn. Yes?
Yeah, I'm asking, maybe I missed some basic point, like where does randomness for neurons come from?
The randomness, so the neurons themselves have parameters in general, just like the A's. Yeah. So if you draw one neuron, you draw the parameters from some distribution, and then one draw of the neuron has some parameters in it that are fixed to some values. If you were to draw it again, they would be different values.
It's just a biological nature of neuron, or like?
No. This is not a biological neuron. This is in the sense of neural networks. So this is in the sense of artificial neural networks, which themselves are random functions based on the way that they're constructed. So there are parameters appearing in neural networks, and the parameters are at any given initialization on your computer, those parameters are drawn from some distribution, and those numbers get plugged. But if you just restarted your code, you'd get a different function because the parameters are different on the next draw.
Can I,
Yeah,
so
sure.
is this just prior to, is there any notion of training or?
I'm not going
is
to train in this talk, but I'm happy to comment on it. Yeah, I'm not going
It's
to.
the initialization is that.
At initialization, indeed, it's random.
Okay.
But if you'd like, even after training, you can think of your trained neural networks as drawn from some trained
Sure.
distribution. And in many cases, sorry, in two very well-known cases, that distribution itself is close to Gaussian. Okay, let's see how the next slide goes. Okay, this one's better. So I'm going to do a very simple example in this talk. The point is that I'm forming my fields out of combinations of neurons via a dot product. The inputs are way down here. In general, this is a picture that you'll see for a deep neural network. And this direction is called the depth. This direction, basically the picture encodes that this is some computational graph that takes simple little functions and stitches them together with some random parameters at the end of the day to produce some field phi. So what I want to do today is give an example of a Euclidean-invariant neuron. I'm not going to prove Euclidean-invariance here. I'll do it in a few slides. The neuron is basically this one. I'm going to call it Li. And this Li is going to be cosine of some parameters, B, drawn from some distribution here. C, we will draw from uniform for reasons that will become clear. And there can be some function f of bi out front that we compute in this way. This sum j runs over these indices, but I is not fixed here. And so given these are the neurons that we're going to build the fields out of. In general, there's no reason for them to be Gaussian, to be drawn from Gaussian, but we can compute correlation functions, again, computing them in parameter space, even if we don't have a description of the action, because we literally construct these neurons by taking draws from some distribution, and so we can compute correlation functions.
Is there any sense in which these neuron functions are a complete basis of functions? I mean, I'm a little worried that if you just kind of have, I mean,
So something that might be useful in related to what you're asking is that neural networks with many activations, including this one, should be universal function approximators. So a classic result in machine learning is that under certain assumptions, any given function can be approximated by a neural network to a given degree of accuracy. So I think you're worried about whether I can get a sufficiently rich set of functions, right?
yeah, I mean, for instance, I think it's important for locality that, at least in near classical field theory, that phi could be like a delta function at any point. That would be an allowed configuration. And I'd want to make sure that you can reproduce that, but I guess you're saying you can.
Yeah, so there's a central interesting dynamics question in machine learning, which is about learning. But a priori, there's these universal approximation theorems that to any given degree of accuracy in the large width limit, that a neural network can reproduce any function. Finding that function with actual learning dynamics is non-trivial, but there's results about this. I should also say that this is just one example. I'm trying to give an example of the more general thing. So this is just one that I wrote down for the purposes of this talk, but it's going to have various properties that I like. So given this way of computing correlators, for instance, I can compute the 2-point function. The expectation value is over the B parameters. You might notice here that I split off, these depend on B parameters and C parameters. I split off the expectation value over B and over C. And this object is something that will be particularly useful for us. But even just directly computing the 2-point function, you can see that this is translation invariant. Furthermore, one can compute the power spectrum, and it takes a particularly nice.
So what do you mean by the power spectrum?
The Fourier transform of the 2-point function. So I have a translation invariant 2-point function. I take the Fourier transform of the difference, and I end up with some momentum, and that's what I.
What about the spectral decomposition? Like, how does it compare to a usual field theory?
Like a Callan-Lehman?
Yeah.
Yeah, so yeah, I mean, in the Callan-Lehman representation, you have this density parameter that you integrate over rho of mu or whatever.
Yeah.
You might need to make some particular choices to be able to come. I mean, that is a very general representation, right? Any nice field theory can have a.
Yeah, but we have some expectations about what a reasonable row of mu would look like. So I'm just curious, like kind of for this sort of, for a kind
That's
of
right.
randomly chosen example, what do you get for rho?
So for this sort of setup, you would have to introduce the integral over the density into the game. For any choices of the parameter distributions and the Fs, you can just compute it. I have noticed I have a large degree of freedom to be able to choose different power spectrums according to different functions F and different choices of B distributions. So, you know, the point would be for any given choice of architecture, which requires choosing a P and choosing an F, you would then want to write the integral over, write it in a form that's of the form of an integral over rho, and it may or may not be something that you like.
Maybe let me just help me understand here.
Sure.
So this Li, this is the same thing that was called Hi on the previous page.
That's right. This is the general story, and I'm going to work here for a little while and then take a single layer
Okay,
case. But
okay.
yes, focus on this neuron for now.
Okay, and what is Bij and what is F of B?
Yeah, F of Bij is a matrix drawn from this distribution, independently and identically distributed. Bi is the ith row of this matrix, and it is appearing here. And I'm allowing myself to have a rather arbitrary function of Bi.
Okay, that's like saying you just normalize the ith function kind of arbitrarily, right?
Yeah, I'm giving some freedom of choice here. You could just set this to 1.
Well, I'm just, it looks very close to Fourier mode decomposition, right? And we know that Fourier mode decomposition of quantum fields is something that we're all familiar with. So I'm just.
Well, so for example, this, yeah, that's an integral over the Fourier mode.
Well, but if you only have a finite number, maybe you'd approximate it by some finite set of frequencies.
Yes, that's true.
Is that what's happening here?
That's probably, perhaps that's one way to think of it. But my point here is that with this setup, I'm giving myself some freedom to engineer the power spectrum in some way that we might like. And I'd point out that also this is the exact 2-point function of these guys here. So indeed, if you, for any concrete choice of architecture, you could say, what is the associated Calvin-Lehman representation? That's right. So this is the example that we're going to play with a bit. The ideas are more general, but this is what we're playing with. Yes.
Can you elaborate what's the role that C play with? Like,
Yeah, C is going to play a very important role. This little thing here, this is the input. This will be playing the role of space-time eventually. This action on the input, it's an affine transformation. In the neural network literature, it's called a linear layer. And so C is called the bias and Bij are called the weights. So this is just some constant, and it will play an important role in a few minutes.
why it should have a different distribution compared to?
I chose that distribution wisely. It gives me translation invariance, which you'll see. So you can choose it to be a different distribution, and you'll end up with a neural network whose statistical ensemble of random functions does not have translation invariant correlators in general. And so this is where the engineering comes in, right? This is the analog of wisely choosing Lagrangians, or in other contexts, wisely choosing other things.
Sorry, Jim, can I just ask again? So curly L is what you were calling phi before? Or
No. This is the
you were
neuron.
calling H before.
I'm gonna do AI Li to get phi.
I see. So then why am I computing correlators of curly L?
Because they'll be related to the correlators of
It's
phi.
linear, phi is linear, no.
Yeah, it'll be related to the correlators of phi. Good. So indeed, this was anticipating it. So what's happening here is that I'm going to take phi to be to this linear combination of fields. Again, I'm taking A from this distribution, and I'm reminding you that I have the neuron of this form. One could have made other choices. In machine learning, this is called the choice of architecture, and this is itself an entire subject. But in this case, because L is just this simple thing, this is what's called a single layer network. So this picture was a more general case of a deep network. But for simplicity, I'm just going to take a single layer network. Yeah.
The Power distribution over the A's is independent of the 1 and the L's.
That's right. They're parameters. They could be the same distribution, but they are drawn independently and identically.
Yeah. So that's what the correlators work out, right?
Yeah. I mean, the computations become harder if they're not IID. That's right. You can still write expressions, but you can't necessarily factorize. Yeah, okay. So this is the simplest choice of a network. This is called a perceptron or a single layer network. You could have, like I said, you could have many neurons and just have Li be the first layer in a deep network. In that case, this is Euclidean invariance that I'm engineering with Li would be inherited by the entire network, provided that the parameters of the subsequent layers are IID relative to the ones at the previous layer. If they're independent, the Euclidean invariance is inherited. Okay. So like I was saying, this is
Are you
this.
saying that you have Euclid, maybe I missed that comment. You're saying that the way you cook this up, you have Euclidean invariance already in the correlator of
The LIs.
of the LIs?
That's right. I have not shown you that result yet. I've just claimed it. I'm focusing on other aspects. That's the next part.
So that's very different than what would happen in a normal mode expansion, right?
Yes. Yeah, that's good. That's a simple way to see it. This is constructing the field in a way where the Euclidean invariance of the entire system is coming from the Euclidean invariance of the LIs. You could just think of this LI as the first layer in a much more complicated function that you would construct. This Li is not a complex exponential. It's not that complicated of a function, but it's a function that I have constructed so that it's correlated.
Cosine.
Huh?
I thought it was a cosine.
I mean,
Isn't it a complex? It's a cosine, right?
it is not a complicated function relative to the full space of functions one might consider. There is this degree of freedom here to choose this. General neural networks are much more complicated than
Sorry,
this.
is it just because you're uniformizing over the shift?
For translation invariance, we'll get there in a second. Yes, uniformizing over the shift is what's going to be relevant for translation invariance. But we're not there yet. So I have this field that I'm forming out of other functions. Yeah. This is how neural networks work. And I'm going to try to make neural nets and field theories talk to each other. Let me keep going. Clay, I think you'll be satisfied in a second.
Keep going.
Yeah.
Yeah.
So the point is that I'm moving to a setup where I'm going to have a simple single layer network where I have I have a d-dimensional Euclidean input. I'm going to, for simplicity, have a single scalar field output, but I'm going to construct it in this complicated way where I have some neurons, these LIs, yeah? And these LIs will run from 1 to n. There's n of them. And I'm going to have a single output. So this isn't the perfect picture. This is 2 outputs. I'll have 1, fine. But the point is I'm then going to take an n towards infinity limit. So this is the picture. And this is maybe another good point to pause and ask, are there questions about the basic setup? I'm forming some random functions in terms of other random functions by taking a dot product. It's that simple. There's nothing about what I've said so far that should make you necessarily think this sounds like how we normally think about field theory. But if we're trying to not do what the machine learning people do, but if we're trying to eventually do some physics, we might like to be able to get Euclidean symmetries into the game. Although they actually do that for computational chemistry, but that's another story. So the mechanism for symmetries is the following. So there's 2 different perspectives on these systems. Normally we think about field theories in function space according to the path integral. But if we have another way to think about the randomness in terms of parameters and how we construct the function, there's a different way to compute correlators. Okay. And so the basic mechanism that we wrote about in this paper, which we submitted to a machine learning conference and it got heartily rejected. I'm happy to comment about that process off video. It's interesting trying to talk to a really different community. But the point is that we can check for symmetries of these neural networks, or alternatively the fields I'm going to call them, by computing their correlators in parameter space, and then checking that the parameter space computed correlators have various properties satisfied under the symmetry. So this was one example from our paper. We act with some rotations on the output here. This is a different case that has some d-dimensional output. And via reabsorbing these R's into the parameters and then having an invariant distribution of parameters, you can show that at the end of the day, you end up with the correlator you started with. So the correlation functions are rotationally invariant. So that's the basic mechanism. So in this case, this is where the shift comes in. So I have one concrete example, I just tell you the result on the other. So we're now going to consider instead, in this example that we're studying, the correlation functions of these neurons could be split into expectations over B that had an expectation over C within it. So this looks like what we had. Indeed, when we transform X goes to X plus D, we can define this B times D plus C to be C twiddle, but the C's are uniformly distributed and we're integrating over 1 period of the cosine. And so this gives you that it's invariant. So this is translation invariance by construction in all of the correlation functions, all endpoint functions. And this is the more fundamental explanation of why the 2-point function that we already saw was translation invariant. Similarly with rotations, because we want full Euclidean invariance, we want translations and rotations. If I have input dimension D, I rotate the x's, and similarly, I use the same mechanism. I study the correlation functions. I redefine some other parameters to absorb the transformation. I change the expectation over this B twiddle, and then the correlators are invariant if and only if P is itself is rotationally invariant, and these F's are rotationally invariant. So the result is that we have a family of Euclidean quantum field theory-like ideas constructed out of these neurons with completely Euclidean invariant correlators for all of the correlation functions. And as I said, I proved this at the neuron level, at the L level, but because the phi's are just functions of those, the Euclidean invariance is inherited. So this is rather different from how we normally do symmetries in quantum field theory. I have a different description of my correlation functions, but I still do the same thing. I check them for symmetries.
Yeah, sorry, can I ask about this again? So imagine I had done a similar thing by just taking a bunch of plane waves. Like I build a random function by summing a bunch of Fourier modes and then
Random coefficients.
average over the wave vectors and phases. I mean, I'm going to get something that's translation and rotation invariant if I average over something drawn from a.
That's what this is.
Yeah, so I'm asking, why is this so different from what we normally do?
When you compute your correlation functions of your fields, you don't think of normally doing it in that way where you have these random parameters that you have. I did a calculation here without doing an action at all. I computed the correlators without having any action in the game. Presumably there is one. I'm agnostic about it now. But yeah, I mean, maybe there's a way to do what you said. And yeah, I think part of the thing here is that I have happened to choose cosines, which indeed is looking like plane waves. I could have chosen any nonlinearity. This cosine is called the nonlinearity in the neural network literature. They take tangents, they take things that have nothing to do with trigonometry, etc. In all of those cases, I could have computed the correlators this way. And that's not normally how we compute correlators in quantum field theory. Yeah. The point is you have an ensemble of random functions described in some way, the randomness in some way, and you want to compute the expectation values. Yes?
So my guess is it will be interesting if you look at multiple layers, because cosine would be a nonlinear thing, right?
Yeah.
So at the moment you're only looking at one layer. That's why everything looks very familiar to Gaussian theory.
That's right. That's a great point.
But when you take it to the, add another layer, then cosine over cosine is a very, very non-Gaussian thing. So
Yeah.
I think that's kind of the theory of like studying, I can sympathize with the way it's done here, because I feel ultimately you want to increase the depth.
You could increase the depth, and indeed you would have to have those later layers would not have to have anything to do with cosines.
Yeah.
Absolutely right.
I mean, I think I can do this in an ordinary field theory. Like if you just tell me the statistics of like the creation annihilation operators or something, I can compute any correlator you want by Wick contractions and stuff. Like why is this different? I mean, I agree that there's some nonlinear function that you're using as a basis, but
Yeah.
I don't see conceptually why that changes the story.
I don't normally compute correlators that way. Do people normally compute correlators that way?
I don't know, but I'm just saying you can. Like
You can. I mean, if you want to call this a something that yeah, I mean, if one, I don't think about field theory that way. If you do, that's totally fine. But yeah, I mean,
okay.
Yeah, I mean, I guess this is not normally how I think about computing correlators. I think about doing it in the path integral rather than based on some parameters that form my function.
But this is more than just like a generalized free theory, though. There's going to be like
It's gonna be not
you
Gaussian.
compute all correlators from the 2-point function. Is that right?
In the large n limit, you can compute all of the correlators in terms of the 2-point function. Indeed, we'll get to that. But these expressions for the correlators are more general, and they're not a path integral expression. They're in terms of these parameter distributions.
But there must be, well, okay, if the AIs are chosen to be Gaussian, then there is some sense in which it is a free field theory.
In the large, that on its own is not sufficient. In the large n limit, phi is Gaussian. And one thing I'll do that maybe will satisfy you, Clay, is that I'll compute the connected 4-point function, and I'll show you that at finite n there are contributions in the connected 4-point function. So that's not a Gaussian theory. Yeah.
So the Hilbert space is not just a Fock space.
I mean, I haven't said Hilbert. This is just an ensemble of functions right now. Hilbert space would, yeah. The theory is only going to be Gaussian if an appropriate central limit theorem holds. And one way we will test that is by breaking the assumptions of the central limit theorem and see how that shows up in non-trivial 4-point connected correlators. Yeah. By the way, I almost didn't recognize you with your long hair.
Yeah.
Good to see you, Austin. Yeah. I was like, I know that voice, but the mask and the long hair. Yeah. Good. Okay, so that's by design. There's a ton of symmetry related work in the neural network literature. Maybe in the interest of time, I'll just tell you that it's out there, and this is beautiful work to look at. If you're looking for a physics application related to symmetric neural networks, I highly recommend this one. This is about using SUN equivariance for lattice GCD.
I think I'm very on Dave Miller and the
Pardon?
Condo. They've been using the stuff for jets.
What's that?
Like a head experimentalist here, Dave Miller.
Yeah, they've
Working
been
with,
using this stuff for jets.
Yeah.
That's cool. Yeah. He's one of the major players in this symmetry area, and of course he's here. So, okay. So here's the Gaussianity story. So this is something that goes by the name of the neural network Gaussian process correspondence. I'll talk a little bit briefly about reflection positivity, and I'll give you 2 examples where I have duality at lower gen. So a Gaussian, yeah, slide issues. I need to figure this out in the future. A Gaussian process, a random function f, is said to be drawn from a Gaussian process if, when it's evaluated on a discrete set of inputs xi, the associated f of xi are drawn from a multivariate Gaussian. Okay. When we take the continuum limit of that definition, we say that f is drawn from a Gaussian process, a normal distribution with mean function mu and 2-point function k, which is called the kernel of the Gaussian process. In our language, it's the 2-point function. The distribution in general looks something like this. And it satisfies this inversion relation where k is the kernel of the GP. The log probability is what we would call the action, and endpoint correlation functions you can think of as computing in function space this way, or alternatively, you can compute them in parameter space as well this other way. So I should say that this is Neil's work. This is this famous work from the 90s. The reason that they were interested is because Gaussian processes is a story about Bayesian inference in the machine learning literature, which is typically removed from stories about neural networks. And what he showed is that in the large N limit, they touch, and we'll get there. But that's a Gaussian process. So our favorite GP, our favorite Gaussian process is a free scalar field theory, and it happens to be translation invariant, which ensures a local action. A priori, an arbitrary GP might be expressed non-locally, but you can still compute the correlators. Okay, so this is how it goes. This is a crucial result. So the neural network Gaussian process correspondence goes like this. This is a single layer feed forward network. So this is a random function. This random function has parameters B1, B0, W0, and W1. The W's are matrices and the B's are vectors. This sigma is called a nonlinearity, and they are drawn as such. And the point is that in the infinite width limit, this here is a little d out by n matrix. In the infinite width limit, this is this matrix here has an infinite number of elements in a given row. And so the output of the neural network is involving summing an infinite number of parameters, IID. This is a case where the central limit theorem is applying. And what we say is that the neural network itself is drawn from a Gaussian process in that limit. That is a Gaussian function space distribution. Okay. So this is the thing where the neural network story starts to sound a little bit like field theory in the sense that generalized scalar field theories are Gaussian processes. If the mean is 0, which we'll take throughout, they're defined by their 2-point function. Furthermore, GP limits are ubiquitous. So the first results were from Neil and Williams in the 90s. This is in 2017 when a bunch of new results started kicking off. And some work of Yang gives a very long list of things, of architectures that admit GP limits. The basic property is that if you're taking a sum of an infinite number of things that are independently distributed, if that's how you form your neural network output, it is going to be Gaussian by the central limit theorem. So the ubiquity of these limits is based on the ubiquity of the central limit theorem appearing with these limits. So let's compute the 2-point functions and the power spectrums. So since the fields are constructed from neurons, the neuron correlators affect the field correlators. This is my neuron correlator here. Indeed, this was computed before. The neuron power spectrum is of this form. And the exact field power spectrum is of this form, where this Li(I2) is this function here. And the choices of the P of B's and the F of B's give you freedom to tune the power spectrum in some degree of generality, so that you can get 2-point functions of different types, and they're all going to be translation invariant. Good. So that is one of the stories here. And this, if you like, since the mean of this process is 0, this 2-point function entirely determines the statistics of the Gaussian process. But because the neural network is drawn from a Gaussian process in the limit, it entirely determines the statistics and correlators of the neural network by Wick's theorem. Am I out of time? Oh, I'm a little bit running out of time. Man, I'm very sorry about the slides. I've never had this happen before with Google Slides. I really don't know what the issue is. So there's this story that Euclidean correlators, given a system, a Euclidean field theory with Euclidean correlators, you can ask what constraints do they have to satisfy to admit a nice, well-behaved Lorentzian continuation and define a proper quantum field theory with unitary time evolution and so on and so forth. So under this equation that got blocked, it talks about reflection positivity. Reflection positivity is a constraint, in this case, on the 2-point function. In the translation invariant case, which is what's under here, the reflection positivity condition becomes of this form. And there's simple solutions to it. Free scalar field theory, of course, is reflection positive. It's a well-defined Lorentzian theory, and you can go back and forth between Lorentzian and Euclidean. And right. So the point here is that because our power spectrum is rather tunable, you can make different choices that will give rise to power spectra that may or may not satisfy reflection positivity. But this is the thing that's related in the Gaussian theory to the existence of a well-behaved Lorentzian continuation. The result is that we are getting a Lorentzian neural network quantum field theory by Wick rotation. The Euclidean symmetry is giving rise to Lorentz invariance in that limit. The unitary time evolution you get by tuning the power spectrum to ensure reflection positivity. And this is in this axiomatic approach, these are the so-called Osterwalder-Schrader axioms, which are the constraints on the Euclidean green functions that are crucial for ensuring that the analytically continued theories satisfy the Leibniz functions. Okay. So just wanted to mention that as an aside, but what I'm trying to do is get these correlators to satisfy the sorts of properties that axiomatic field theorists who are concerned about things having a proper analytic continuation would want us to. So the reflection positivity is actually a nice, simple little calculation that can be done. Basically, it's a simple study of the Hermitian adjoint of operators in Euclidean and how that correlates with proper unitary time evolution in Lorentzian, and then the existence of non-negative states imposes this condition, basically. So this is something that's standard and in textbooks. Okay, so that's nice. So if we want to use these sorts of ideas to actually do field theory, not just in Euclidean, we need to have these sorts of properties. Okay. The other thing that I want to mention is a large N duality. So this is something that we're looking at in follow-up work, but we haven't studied in the literature yet. So in the particular choice that I take F is equal to 1, and I take this distribution P to be a normal distribution with some particular variance. This is a particular specialization of the set of examples I've been discussing so far. The 2-point correlator just takes this form, the power spectrum. It's some Gaussian. But we had another architecture last year that at large N also had a Gaussian power spectrum. So up to redefinition of these various constants to make the Gaussian power spectra exactly match. What this is saying is that these are two very different neural network architectures that nevertheless, in the infinite limit, give rise to the exact same Gaussian process, which is a duality. Right? If all of the correlators match, it's a duality. So you might try to do that more generally with other architectures at all values of n the width. But the result here is that though these two architectures are dual at infinite n, they're because they're giving rise to Gaussian processes with the same 2-point function. At finite n, duality does not hold. In particular, you can compute, for instance, the 4-point connected function, the connected 4-point function, and just see that they disagree. And furthermore, the symmetries don't match. This happens to have a translation invariant 2-point function, but the higher correlators are not invariant under translations, whereas this gave rise to a translation invariant system by construction. So at finite end, the duality does not hold. The 4-point connected functions just disagree, and furthermore, the symmetries don't match. So this is a case where you could imagine trying to study these two examples and perturbing away from large n and seeing how the presence or absence of the symmetries in the system affects the correlators. But this is a large n duality. That's my point. Very different looking neural network architectures give rise to the same statistics at infinite n, but not at finite n, and they even have different symmetries. Okay. Any questions on Gaussianity?
I think you started 10 minutes late. So.
Oh, I did. Okay. Yes.
So can I ask us a more broad question? So if the way I understand it is that you're basically starting to build this, from the bottom up, right? Instead of looking at symmetries like Lagrange, you say, can I basically build in this? Can I build in that?
Yeah, exactly.
And then you understand something about the large n limit,
that's right,
when it all goes to Gaussian.
That's right.
And I guess you will understand something about the the finite limit when it's not. But what is the, let's put it this way, what is the, and some of the questions that were going before were effectively pointing out that, one choice for your basic unit could be basically plane waves, right? You could basically play the same game with the plane wave, but you have the freedom to play with all sorts of more complex things, right? What is that you will gain at the very end of this? You have this freedom, you're constructing those examples which you can, let's say, build a, theory with a certain amount of symmetries that works in a finite end limit and so forth. Okay, you have that stuff.
Yeah.
What is your ultimate goal? Do you think that this will help you, computationally or conceptually you will discover a certain new class of things? Yeah, I think that's maybe what I'm not exactly getting.
Yeah, I mean,
or let's put it, do you explore this out of curiosity, or do you actually have that sort of specific goal in the mind to say, if I can construct this kind of theory which kind of works in the finite end limit, when I take, let's say, the basic units not to be plane waves but some deep networks, that's going to be super good for application of specific application.
Yeah, I mean, okay, good. So from an application point of view, I mean, generally the rule of thumb is ensembles and more complicated networks are going to be better for training. So if one of the concerns is at the end of the day to use these sorts of stories to actually do machine learning, complexity is going to help the game. I mean, in some sense, I am exploring it out of curiosity, and as a theorist, I do not apologize for that. But in some sense, these other things that are not just plane waves are themselves ensembles of random functions that are not, in general, they are not, and they're just density over functions to the extent that you can really define it and write it down, doesn't have any reason to be anywhere close to Gaussian, period. And that's part of my interest in it. Part of my other interest in it is just to try to understand the different ways in which physics and machine learning are talking to each other via these neural networks. But indeed, I mean, you could take simpler ansatses for these functions. As you know, much like in the literature, neural networks get significantly more complicated than the ones that I'm doing. And the basic statement is that in many cases, these are drawn from.
I mean, fair enough. Curiosity is a good enough motivation. I was just wondering whether you have a specific strategy to follow to the end, because you have a, let's say, computational goal of some sort, or
Yeah, I mean, I'll
I mean, your answer is perfectly fine.
Those are some of the reasons that I'm interested in.
Okay, thanks.
So let's talk about interactions. So the Gaussianity in these setups follows from the central limit theorem, which requires an independent infinite sum. So the idea is that breaking the assumptions and not having a central limit theorem anymore should give rise to interactions, because you have non-Gaussianities in the function space density. Even if you don't know what the function space density is, we know that the Gaussianity is ensured by the central limit theorem. So if we break the central limit theorem, we should have connected 4-point correlators. Okay. So here's what I do here. In this case, I have the fields from the neurons here. The fields from the neurons are constructed. I'm being more general here. I'm sorry. This is the general result, not specific to this example. I should say that. So now I'm just taking these neurons and I'm constructing my fields out of them. This is the 4-point neuron correlator. This is the 2-point neuron correlator with this shorthand. And when you compute the connected 4-point function, what you find is that there's two different types of interactions that arise. There's this type of term and this type of term. These types of terms are finite end corrections. So at finite n, you end up with contributions to the connected 4-point function of this form that have various 4-point correlators and products of 2-point correlators subtracted off. Notice that they're 1 over n suppressed, so as n goes to infinity, as you regain that assumption of the central limit theorem, these go to 0. And finally, there's what I call independence breaking corrections. This is something that is not in the normal literature, but it's obvious that this should be the case. If you don't have independent variables, then the central limit theorem doesn't hold either. And in particular, you can compute this other contribution. The key thing to notice is that these pair up, and these pair up, and these pair up. And these correlation functions, this HII, splits into be exactly this in the limit that the II and JJs are independent from one another. So in the limit that you restore the independence of the parameters, you can break the central limit theorem by either breaking infinite n or breaking independence, and you get these sorts of contributions to the connected 4-point function. So this is a nice story where you literally take this setup. This is an exact expression for the connected 4-point function in these setups. Gaussianity, in the Gaussian limit, this has to go to 0. That's the connected 4-point function is 0 in a Gaussian process. So when you compute this exact expression, you see that there's 2 different types of terms that arise, and they directly correlate with breaking the central limit term. In this particular case, I guess I have 5 or 10 minutes left, but I want to take more questions. The non-Gaussianities in this particular example, this is just a copy of what was on the last slide. The H's in this very general setup are what I was calling the L's I'll talk. So this is in the example. And indeed, we can compute the connected 4-point functions. This x plus plus minus minus is x1 plus x2 minus x3 minus x4. Indeed, it's all translation invariant, it's all rotation invariant. And this is applied in this example. So given this general expression in any given example, you can compute the connected 4-point function. Okay. So in our first paper, we modeled interactions in a Lagrangian and compared to neural network experiments. Here are the points the opposite, where we're trying to do everything directly in parameter space, and we want to compute we want to have integral expressions which we may or may not be able to evaluate in general, that are the exact interactions in parameter space. So there's ongoing work with Matt Schwartz and with my students exploring function space interactions that reproduce these theoretical results computed in parameter space. Okay, so one nice thing about this, let me review. So in summary, what we're doing is we're taking some neurons, which are these random functions H. I gave a particular example where I called the H's L's. I am taking a sum over with parameters up front, taking a sum of n of these neurons, and in the large n limit, these things are drawn from Gaussian. At finite but large n, therefore, you should have weak interactions, and these G4Cs should be relatively small because they're 1 over n suppressed. Okay, so I guess the way Austin thinks about this is not a different origin of randomness. Fine. It's not I am not computing correlators in the path integral. That's a critical point. A priori, I do not know the function space density associated with these neural networks. I don't know the action associated with these neural networks, and nevertheless, I can compute correlators. If you can actually evaluate those integral expressions, I would say those are exact correlators that are not computed in perturbation theory in any way, shape, or form. This is non-Lagrangian and non-perturbative. If you make wise choices of the architecture, those field theories can satisfy the Osterwalder-Schrader axioms, which ensure that the Wick rotation gives a Lorentz-invariant unitary theory. And finally, interactions arise by breaking the central limit theorem. If Gaussianity is arising by the central limit theorem, if you break the assumption, you get interactions. Okay, and I showed that explicitly. So some output of this is that when you build fields out of neurons, the neurons in general are not drawn from a Gaussian density on functions, but the sum of them by the central limit theorem is. And so in this context, this is a setup where when you build it out of neurons, the QFTs are nearly Gaussian. Something that I haven't studied enough, but is worth saying, is that you can, in this context, you can study mixed field neuron correlators. So I just I'll talk about the neuron correlators or the field correlators themselves, but there's no reason to stop you from computing the mixed correlators. And there's questions about that I won't get into. And a potential use case is for lattice field theory. So there's truly awesome work using machine learning for lattice field theory that I am happy to tell you about in as much detail as I understand it. It's not something that I work on, but I'm really excited about that work. This is a different construction. The whole point of that of general lattice field theory about what's hard and also about what people use for machine learning is that there's a sampling problem. Given a Euclidean action that you want to sample from, QCD for instance, you want to have a faithful sampling of gauge fields from the right density on functions that you can trust and then compute observables and take to the bank. So this is a different construction from that, where the sampling is easy. I literally just fire up my code and construct the function, but the action is not a priori known. So in a case, I mean, maybe this is one answer to your question. To be a little pie in the sky for a moment, if you could come up with an architecture whose statistics exactly gave you the QCD action or some other simple scalar field theory action that you care about, you could use this sort of technique for lattice field theory. And you wouldn't have to do the Markov chain Monte Carlo. Does that help with a potential application?
But in that case, you would need to build a lot of things into the distribution of your parameters, right?
Oh, for sure. We're not nearly there. This is very much first steps. Yeah. So given the things that I wrote down today, you could just say this is a theory. Let me put it on a lattice and compute observables. But if you have a particular physics theory that you want to compute, where by particular theory I mean we know the Lagrangian we care about, then you have to work hard to give an architecture that does that.
And do you have a sort of an idea how would you go about fixing your architecture, your parameter distributions, given the fact that there is a target?
So one thing that I would say is that I already gave you a way to do symmetries. If I'm trying to engineer an architecture that gives a function space density that I care about for physics reasons, and I know the symmetries of that thing, I can use this computation in parameter space and the fact that the correlation functions are symmetric in parameter space, and that gives me a guide. So there's a way to correlate what is happening in the architecture and what it means for what's happening in the Lagrangian. That was the point of our paper. It's not nearly there yet, but certainly symmetries are one of the first things that you would try to tackle if you wanted to be able to engineer these things. So put differently, that's what I mean when I say we have some design principles. So that's it. I'll take more questions. I ended 5 minutes early. Thanks a lot. Admittedly, this is the first talk I've given on this particular work. I've talked on this subject many times. This different angle, thanks for being the first people to hear about this and guinea pigs, if you will. So thank you very much. Yeah.
Could you say a bit about, you referenced a paper on learning knot invariants?
Oh, yes, sure. Completely unrelated, but what is it?
In the sense that, is it like these knot invariants also, like, if you give me a way to produce knot invariants, there's interesting symmetry. So are you encoding those in the neural networks you're building?
So no, and furthermore, my work thus far has not, there are other works about ML for knot invariants. There's also various things you want to do to a knot, which is another thing that topologists study. So we solved something called the unknot problem, which is related to something called the slice problem that we're working on now. And basically there, the idea is that there's a sequence of operations that you can try to do to a knot to unknot it. And that's what we did. So we weren't computing invariance, we were trying to find the sequence of moves that unknots it. But there are also works, to answer your question, that are about ML for knot invariance. And to my knowledge, they have not yet tried to bake in symmetries. Yeah.
Can you talk more about how to realize a gauge symmetry in neural network?
Oh, I don't have useful comments on gauge symmetries here yet, and as Clay would point out, gauge symmetry is not a symmetry. but we just had a discussion at lunch about this. But indeed, I mean, if you wanted to do something like that here, you would want to have some sort of way that there's a redundancy in the system where some analog of gauge fixing in the path integral, which we do not have a path integral, where there's some analog of gauge fixing here. There are papers about gauge equivariant neural networks that are back there, but it's a little different from what I'm doing. Yeah.
It's fine if you don't have an answer for this, but fermions?
Yeah, right. So good. So there are free fermions, and one might call that a Grassmann Gaussian process. And so to do this, you would need to have a Grassmann valued neural network that in some limit gives rise to a Grassmann Gaussian process. We do not have results that are major on this yet. It's something we're thinking about. It's interesting. Naturally, you might imagine that machine learning people are happy to consider real valued networks all the time, but are not regularly considering Grassmann valued networks.
But there is some literature on such things. Sorry, that's a question.
So good. People do various things with fermions, but there is, to my knowledge, They do it in different sorts of ways. It's not this Gaussian process stuff. Yeah. Yes.
It seems at least in the case of like the family of functions on 4 Grassmann variables is a much smaller class.
Sorry, say it one more time.
Like the family of functions over Grassmann variables is a much smaller like object than the real functions, right? So maybe it's more tractable because of it. Or not
I
necessarily.
guess I don't have a comment. So maybe it's worth saying, since you guys are asking about other possibilities, one thing that is pretty easy to do is end up with an n-dimensional scalar output. Or I shouldn't call it n because I had another n, capital D dimensional scalar output, and to engineer SOD symmetry. So you can do things like that for sure.
How can you ensure that the field theory you build is in the string landscape?
That's a completely different line of my work that has nothing to do with this a priori. Or maybe, yeah.
That wasn't a serious question.
Yeah, I have a paper on archive tonight that's totally different from this stuff. Felt good to do some string compactification.
Any other questions? No, let's thank Jim again.
All right, thanks a lot, everyone. Appreciate it. If you have more questions or want to talk about anything else, feel free. I'm around tomorrow also. I guess I'll let you have things here.
Can you set up an invisible?
Yeah, that's right. That's right.